while you're doing these two wonderful warm-up problems, finding the perimeter of a sector of a slice of Toledo's tasty goodness, chicken bacon ranch is the only one to go with, just so you know. Okay, all right. And the area of this slice of pizza. Just a reminder that this week, Friday, you will have another formative. Yesterday, you took a formative in class, and on that half-sheet formative that you took yesterday, we will be giving you full credit back on that one. Okay? So, but normally, starting with Friday's formative, fixes will only be half a credit or half a point back. Okay? So if you get too long on Friday's formative, the most points you can get back would be 1 point. Then, okay? Half of that. Okay? I have been complaining for a week and a half. So.
Sure, order.
When did you say we get our tests back?
Next Tuesday. All right, here we go. Perimeter, slice of pizza. Yes, slice of pizza. Okay, so this top part is going to be S equals theta R, or R theta works for me. Yes? What are the sides going to be?
14.
They're going to be R, right? Okay, so that's going to be 14. That's going to be 14. And this is going to be, so how many slices do we determine? 8 slices in a pie? That means each of these is going to be 45 degrees, but more importantly, each of those is going to be pi over 4 in terms of radians. Okay? So 14 times pi over 4 plus 28. So that's going to be 7 pi over 2 plus 28 inches. Agree with that. What's up?
How do we fix the calculator to make it show the fraction version, not the rounded decimal?
You type it in as a fraction.
Yeah.
Can't use pi.
Can't use pi?
Nope. So you just have to type in 14 divided by 4.
Okay.
Okay. All right. Area of that sector. Whoa, Nelly. How much of the pizza do we have? We have 1/8 of the pizza. Oops, got the brakes. What is the area of the whole pizza? What's the area formula for a circle? Pi r squared. Okay, so this would be pi times 14 squared. Yes? 14, so that's, I mean, if I'm doing this without a calculator, that's going to be 1/8 times pi times 14 times 14. 2 is going to go in there. Oh, not 2 is going to go in there. 2 is going to go in there 4 times. 2 is going to go in there 7 times. 2 is going to go in there twice. 2 is going to go in there 7 times. So I get 49 pi over 2 square inches of tasty deliciousness, savory goodness. OCD's kicking in. Questions, comments, concerns, clarifications? Love it. Schmeling. This is where Schmeling this morning. He was supposed to bring the scooter in, and he didn't bring the scooter in. Okay? So Schmeling is cruising on the new electric scooter at a maximum speed of 15.5 miles an hour around the mean streets of Wausau. At this speed, how many revolutions per minute are the 8.5 inch diameter wheels rotating? Okay. Go for it. Oh, I know.
Oh wait, never mind. I'm so sorry. I'm so sorry. I did not know that. Oh
$15.5, 5,280, 12, 60, 4.25, and 2 pi. There. Yes? No, yes. 5 times
The MI, that's
80
times
times 12, 60 times 5 gives me, I get 612.952 RPMs. Yes? Miles, miles, hours, hours, feet, feet, inches, inches, radians, radians, revolutions per minute, yes. Questions, comments, concerns, clarifications?
How do you know what to start off with?
You're always given it in the problem. So you'll be given some kind of speed in the problem. Okay? Usually pretty early. Okay? And then it always tells you where to go to in the end. Yep. So you keep going until you get there. Okay? All right, let's do it. Here we go. The belt on an electric motor connects metal wheels with radii 2 inches and 5 inches. Rotational speed of the larger wheel is 120 revolutions per minute. We'll get to a bike problem here in a minute, but the bike chain and the bike tire also represent this. So what's basically this is saying is this sprocket back here on the back side of the bike is the 2-inch radius sprocket, okay, or wheel, if you will, and the crank shaft or the crank pedal or the crank sprocket is the larger one. Okay, so as it's spinning, are they spinning at the same? Let's talk speed. We have 3 different speeds here. Okay, so are they spinning at the same angular speed? Are they spinning at the same rotational speed? No. Okay. Are they spinning at the same linear speed? Think about those for a second now. Okay. So, rotational speed, this one obviously is spinning much faster, correct? Okay. Okay, so that one's spinning much faster, so rotationally they are spinning at different speeds. Angularly, if this one's spinning faster, are they spinning at the same angular speed? No. Okay? Linearly, are they spinning at the same speed? Yes or no? So, Mace, you said no. Okay? So what's connecting them? In this particular case, it's a chain, right? Up here it's a belt. Same thing. Okay? Is that belt moving faster here than it is over here? It's the same belt, right? So can this belt be moving faster over here than it is over here? No. So the constant that it's doing is linear speed. Okay? So if you are going to go from one sprocket to the next, the only way that you can go there is if they're connected. And the only thing that's connecting them is on a bike, it's a chain. On an electric motor, it's a belt. Okay? And so you have to get to linear speed to go to the other side. I'll say that again. If you're on one sprocket, you need to get to the other sprocket. The only thing that connects them is the linear speed. Okay? Okay? So, a belt is the rotational speed of the larger wheel is 120 revolutions per minute. Knock. There it goes. Okay? So we're spinning at 120 revolutions per minute on the big diameter sprocket or wheel. Find the angular speed of the larger wheel in radians per second. Okay? Well, what do I have to multiply by? To go from rotational speed to angular speed. Okay, I need 1 minute and 60 seconds because I got to get it into seconds. What else? Now I'm in revolutions per second. Two pi radians over 1 revolution. That's it? Because now I'm in radians per second, which it told me that I needed to be in. Okay? So, all told, this becomes 120 times 2 pi divided by 60. So that would be 4 pi radians per second. Agree with me on that? So every second, this smaller wheel is going around how many times? How many revolutions is it making? 2. It's making 2. Okay. Oh, sorry. That's the belt. There. Sorry, that's the big wheel. Okay, the big one, because we're still on the larger one. Okay. What is the linear speed of the belt in inches per second? Well, we're already going 4 pi radians per second on the big wheel. Yes? Okay. What is the radius of the big wheel? Of the big wheel? 5 inches, right? 5 is bigger than 2. Okay, so the big radius would be 5. Okay, so then that's going to be 1 radian is 5 inches. So this is going 4 pi times 5 divided by 1. So that's going 20 pi inches per second. That's the linear speed of the belt. Okay? Now we can follow along on that. So now let me start spinning here again. So now we're spinning around, and okay, I can't even get it going 2 revolutions per second. Okay? All right? So now we're spinning around. Okay? We're on the belt, which now allows us to go from the big. So far we've done nothing but big wheel here. So now we can go to the little wheel, because the little wheel is also spinning around at 20 pi inches per second. Because this belt doesn't speed up on this side and slow down on this side. That belt is one belt. It's traveling at the same speed all over. Okay? So my angular speed here then, for the smaller wheel, I'm going to start with that it's at 20 pi inches per second. Now the smaller wheel is in a 2-inch radius wheel. So that is my conversion, 1 radian over 2 inches. So the smaller wheel is spinning at 10 pi radians per second. So as you can see, it's the same setup here. The larger wheel is spinning at 4 pi radians per second. The smaller wheel is spinning faster because it's spinning at 10 pi radians per second. Linearly, they're spinning at the same rate, or they're moving at the same rate. Angularly, the smaller one is spinning faster, which also would mean that we could go one step further. Now I'm at 10 pi radians per second. And I can say that 1 revolution is 2 pi radians. Okay. And then I can multiply. What was our first one? It was in minutes, right? It was spinning in RPMs? Yep, in RPMs. Okay. And then I can multiply by 60 seconds is 1 minute. So now we get 10 pi times 60 divided by 2 pi is going to be, what is that, 300? RPMs. So the big one was spinning at 120 RPMs. The small one is spinning at 300 RPMs. So in terms of speed on 2 different size connected wheels, the only thing that's constant is the linear speed of the belt or chain that's connecting them. Angular and rotational are both different, unless they're the same sized sprockets. Okay? Try that one. So the 4-inch pulley is spinning at 1,450 revolutions per minute. So I need to multiply that by 1 revolution is 2 pi radians, and now I'm in radians per minute, and so that is going to be 2,900 pi radians per minute. Agree with me on that? That's the 4-inch. Now, we have the 9-inch. The only way I can get from the 4-inch to the 9-inch is by what they're connected with. In this case, it's connected by a belt. So I need to find the linear speed of that belt. So I know that the 4-inch is spinning at 2,900 pi radians per minute. I know that the 4-inch has a radius of 2 inches. So that belt is currently spinning at, what would that be, 5,800 pi inches per minute. And that's the linear speed of the belt. So now I can go from the small pulley to the larger pulley because I've got the linear speed of the belt. Okay? But now then I've got to bring that back, that linear speed. Now I'm on the big pulley. I got to bring that back in. So I'm going to multiply by now 4.5 inches on the bottom is 1 radius, or excuse me, 1 radian of the larger one. $2,900 times 2 times 2 divided by 4.5 gives me 11,600 divided by 9. Oops, I forgot pi. Radians per minute. If it was a fraction, if it was a decimal, it would be approximately questions, comments, concerns? Yes.
Well, I didn't know what type of go did we got 1280 and 8. Yeah.
2,900. Oops, I'm gonna clear this out. 2,900 times 2 is 5,800. Divided by 4.5 is that. Times pi is that.
How is it 9 on the ball?
Because that's what this fraction reduces to. Yeah. You can divide them both by 0.5.
I did not get it, no.
Did you set it up the way I set it up? Because if you didn't set it up the way I set it up, you're not going to get my answer. You understand what I'm saying? Like, so did you start with the 1,450 revolutions per minute, or did you start with the answer that you already had?
I started with that one.
With this one? Okay, so that's where I started.
Yep.
So that's radians per minute of the smaller one, right? Okay, need to get to linear speed. So the 4-inch diameter is 2 inches over 1 radius, which is 1 radian. Okay, so it's 2 inches over 1 radius, or 1 radian. So now I'm in inches per minute through here, right? Which is a linear speed of the belt that's connecting the two. So now I can jump to the other one, which is also moving at that same linear speed. So then I have to switch that back into radians per minute. Now I'm on the bigger one. So that's going to be 1 radian of the bigger one is 4.5 inches. So I have to take this 5,800 pi and divide it by 4.5, which gets me 4,049.164.
I think you put it in your calculator as 45 and not 4.5.
Nope. Because you divide them both by 0.5. So 4.5 divided by 0.5 is 9.
Oh, yeah.
Okay. 5,800 divided by 0.5 is 11,600. Yep. Yep. Find the speed of the saw in revolutions per minute. Well, now that's where I'm starting. So now I'm on the saw, so I'm on the big one. So that's going to be 11,600 pi over 9. And that's radians per minute. And I'm going to multiply that by 2 pi radians on the bottom, 1 revolution on the top. So that's going to be 5,800 divided by 9 revolutions per minute. Pi's cancel out. 2 goes into 11,600, 5,800 times. Helps to know how to do fractions. Okay. Questions, comments, concerns? What's up?
If this was like a test question, and so like for the 4,049, if we left that in exact form, so like,
If you left it as this one,
yeah, or like,
I'll take exact form every day and twice on Sunday. Yep, 100%. 100%. Sometimes the exact form is just not, easy. Like yesterday we had the 2.54 centimeter conversion one. That one's never going to be exact because it's going to be it's a goofy fraction. But this one, very much so. Okay, let's do one more. How far in feet? So if you've ridden a bicycle before, you turn the pedals, the wheel spins, and you go forward. Right? Okay. So my question is, how far in feet will the bicycle move if the pedals are rotated through 3 full rotations? Assume the radius of the bicycle wheel is 13.2 inches. You're going first, you know what I mean? So 3 full rotations. After you get to that 3rd rotation, we put a mark on the ground, we measure that distance. Yep. Okay. What am I going to start with? What do I have as my one measurement? What do you got?
you just find the perimeter of one of the circles.
But what do I have though?
Oh, the radius.
Because the wheel's not going, the tire's not going around 3 times. The pedal's going around 3 times. Okay? Alright? So what do I have as my starting measurement? Nope.
7.45.
Nope. What am I doing? What are we doing in this scenario? Three full revolutions on the pedals, right? Okay? So I've got 3 revolutions. That's my start. 3 revolutions. Okay? 1 revolution is how many radians? One revolution is how many radians? 2 pi. Because where do I need to get to? So right now, I'm sitting on the pedals, right? Where do I need to get to? I need to get out here to the edge of the tire, right? Okay? I'm here right now. How do I get there? Got to get to a linear speed of this chain, right? Okay? So right now we just went from rotations to radians, correct? Okay? Radians, then we can go to 7.45 inches. What do we have right now? We don't have a speed. Because I don't have any time. I have how far what? Because right now we're at a linear, right? Because we're at, revolutions are gone, radians are gone, so I'm at inches. What have we just figured out? Distance of the chain. So we figured out how far the chain went, right? Did the chain travel the same amount? So this orange piece right here, did the chain travel the same distance here as it did down here? Yes. Okay? It traveled the same distance. The linear is constant in this scenario. This one can't go faster or slower than this one, and the chain can't go farther over here than it did over here, because it's one chain. Okay? So I'm at the distance that the chain went. Now I can go to the smaller sprocket. Yes? Okay? So the smaller sprocket is 2.52 inches is 1 radian. So now I have this was all on the big pedal. Now I'm on the small sprocket. And I have how many angles or how many radians that this one spun. Correct? Okay. Is that the same? Now I want you to watch the red piece of tape here and a rotation to where how it's spinning on the sprocket. Notice how I should have put a dot. Did I put a dot on that sprocket? No, I didn't put a dot on that sprocket. That rotation is spinning at the same rate, correct? Because it's going around the same axle. Okay? So the rotation of the sprocket is the same as the rotation of the wheel. See that? Okay? So that means I have the angular speed of this, or the amount of angles that the sprocket went through, but I also have now the angles of the wheel. So now I'm to the wheel. We went from the pedal to the chain to the small sprocket out to the wheel. We have to stay connected. We can't just jump from the pedal to the wheel because they're not connected. Okay? We went from the pedal to the chain to the small sprocket to the wheel. Okay. So I'm in radians now of the wheel. The wheel has a radius of 13.2 inches. We want it to be in feet at the very end. So I need to switch my inches into feet. Radians cancel out radians, inches cancel out inches. I'm left with just feet. So on top, we have 3 times 2 pi times 7.45 times 13.2. On the bottom, we have 2.52 times 12. Stop it. There we go. 3 times 2 times pi times 7.45 times 13.2, 2.52 times 12. I'm not even going to try and do this one in a fraction. So this is 61.299 inches. Oh, sorry, it's feet, yes. Feet. Good times? Good times. You can be through number 20 in your homework packet. And I strongly recommend that you be through number 20 in the short future in your homework packet.